Now, constant pressure or coffee cup calorimetry works great for reactions in solution, where there's no major volume changes during the reaction. In terms of, the reaction doesn't, after you've added everything in, it doesn't go from like 10 milliliters all the way up to 1,000 milliliters or something like that. But what about reactions that aren't done in solution, something like combustion reactions, where there might be a large change in volume because we might produce a large number of gases, and there might be some changes there. Well, there's a second type of calorimetry known as bomb calorimetry, and this is for cases where if we were to keep the volume constant, which we do in a small cylinder, that now the pressure in the system would no longer be constant. So remember, we defined enthalpy as being the heat at constant pressure. Well, now we have a case where there's variable pressure, where the pressure before the reaction and afterwards would be different. Well, what we can do in the majority of cases is that often that change in pressure does need to be accounted for by some other calculations, but normally the contribution from that change in pressure is fairly minimal. And so in many cases, we can simply equate the heat under variable pressure to the heat under constant pressure, unless the changes are very extreme. And so we can still assume that enthalpy is just equal to heat change, or the heat in this particular case. However, our equation for a bomb calorimeter looks a little bit different. So it's, rather than being the specific heat times the mass times the change in temperature, it's now the heat capacity of the whole calorimeter times the change in temperature. Where does the mass go? Well, the mass is taken into account when we measure the heat capacity of the calorimeter. So any bomb calorimeter will be calibrated to determine its specific heat capacity, and the mass of the calorimeter is taken into account when that measurement is made. So as long as we know the heat capacity of the calorimeter, then all we need really is the change in temperature to allow us to get to the enthalpy. Remember now that the calorimeter is the surroundings, and so it absorbs the same amount of heat, but the sign is now opposite from the actual reaction. Delta H is the enthalpy for the reaction, not the surroundings. So the sign is opposite. Okay, so let's do a specific example. Say we had a 2.200 gram sample of quinone, which we're given the chemical formula for. It's burned in a bomb calorimeter whose total heat capacity is 7.854 kilojoules per degree Celsius. The temperature of the calorimeter increases from 23.44 to 30.57 degrees Celsius. So what's the heat of combustion per mole of quinone? What the question is basically asking is, what's the enthalpy in terms of kilojoules per mole of quinone? Okay, so we're given the heat capacity, and we're given the temperature change, so we can determine the enthalpy here directly in terms of kilojoules. So we simply take the heat capacity, substitute that in, times the change in temperature, plug that in, and we come out, if we keep track of our units, we come out with an amount in kilojoules. But we've been asked for that on a per mole. So we want kilojoules per mole. Well, just like the example in the last video, when we're trying to find something per mole, we were given the mass, and we're given a chemical formula. We can use the molar mass to convert mass to moles, and then we can simply take kilojoules divided by the number of moles to get it in kilojoules per mole. So 2.200 grams divided by the molar mass here, which is just summed up the atomic weights of quinone, and I come out with 0.02035 moles of quinone. Now I've got kilojoules, I've got moles. I simply take the amount of kilojoules divided by the number of moles, and I come out with negative 2.75 times 10 to the third kilojoules per mole. Okay, so we've done constant pressure calorimetry, we've done a variable pressure or a bomb calorimeter. Now let's just work through a couple examples of how you would solve problems that involve calorimetry. So let's take this first one. We've got a student mixing 50.0 grams of HCl and 50.0 grams of sodium hydroxide. They're both aqueous solutions. It's in a constant pressure calorimeter, so I know I'm in a coffee cup calorimeter, and I know that I need to use the equation that corresponds to that. The temperature of the solution increases from 22.0 to 27.4 degrees Celsius. What's the enthalpy in kilojoules for the reaction? And the specific heat of the solution we're given as 4.18 joules per gram degrees Celsius. Okay, first off, enthalpy for my formula for this must be delta H is equal to negative specific heat times mass times delta T. All right, so I know that my specific heat is the 4.18 joules per gram degrees Celsius. My mass is the total mass I've got present, 50 grams of the HCl solution, 50 grams of the sodium hydroxide solution. So my mass is equal to 50.0 plus 50.0, 100.0 grams. Then my delta T is always final minus initial, so that is going to be 27.4 minus 22.0, and I come out with 27.4 minus 22.0. Looks like we have a temperature change of 5.4 degrees Celsius. Okay, so we've got everything that we need for this. So we just plug it into our equation. Delta H is equal to negative 4.18 joules per gram degrees Celsius times a mass of 100.0 grams times a temperature change of 5.4 degrees Celsius. And if I go down here and just switch colors for a moment, so grams are going to cancel, degrees Celsius cancels. I multiply this through, and I will come out with now, it's going to be a negative number, 4.18 times 100 times 5.4. I come out with initially negative 2,257.2 joules. Now, I'm not done yet because I've been asked for this in kilojoules, not in joules. So I can do that conversion really quickly. There are, for every 1 kilojoule, there's 1,000 joules. So joules cancel. Simply divide this number by 1,000. And I come out with 2.2572 kilojoules. Now, I have to go back at this point, go back to my equation and figure out how many significant figures I'm allowed to have. Turns out back in this equation that 5.4 only has 2 significant figures. So I must be limited in my final answer to 2 significant figures. So I can round 2.25 just to 2.3 kilojoules and choose that as my final answer. Second problem here is a case of a bomb calorimeter. So we've got 1.800 grams of phenol. We're given the formula for that. It's combusted in a bomb calorimeter where we're given the heat capacity. And we're asked, what is the heat of combustion in kilojoules per mole if the temperature goes from 21.36 to 26.37 degrees Celsius? All right, it's a bomb calorimeter, so I need to figure out, I'll write out the appropriate calorimetry equation. So delta H is equal to minus C for the calorimeter times delta T. Well, I'm given C and delta T. I should be able to figure that out fairly easily. So delta T is going to be just 26.37 minus 21.36. And I come out with 5.01 degrees Celsius for the change in temperature. I can just plug these values in, and negative 11.66 kilojoules per degree Celsius times 5.01 degrees Celsius. My degrees Celsius cancels, and I come out with 11.66. I come out with 58.4166 kilojoules. Now, I haven't been asked for it in just kilojoules. I've been asked for it in kilojoules per mole. I need to figure out how many moles of phenol that I have present. So I have 1.800 grams. So let's put that over here, 1.800 grams of phenol. And then C6H6O. Well, I add up those atomic weights. So carbon is 12.01, so 12.01 times 6 plus hydrogen is 1.01, so 1.01 times 6 plus oxygen is 16. And I come out with 94.12 grams per mole. So the moles go on top, 1 mole, 94.12 grams. Grams will cancel. And I come out with now 1.800 divided by 94.12, and I come out with 0.0191245, just carrying all sorts of extra digits, moles of the phenol. What I need to do now to get my final answer in kilojoules per mole is I simply take the number of kilojoules and I divide it by my number of moles. I can carry the extra decimal places now. I'll just account for it at the very end. Moles. Multiply this through and take the 58.4166, divide it by the number of moles, and I come out with 3,054.539. But now at this point I can go back and say, well, I only have 3 significant figures in the calculation of delta H, so I'm going to round myself off to 3 significant figures, and I'll write it in scientific notation just to help. And so I'm just going to direct this over here just so I have a little bit more space. 3.05 times 10 to the third kilojoules per mole. And that's how I would solve a calorimetry problem like this.